I'm going to finish up nitriles, which will finish up this, and we're going to talk a little bit about synthesis. So we were talking about reactions of nitriles and hydrolysis. We can also look at hydrolysis under basic conditions. And of course, we're going to hydrolyze the nitrile all the way to the carboxylic acid. We don't lose any carbons, but we do lose that nitrogen. So as far as which group is the nucleophile and which is acting to protonate the nitrogen, we should look at that. Of course, we're going to attack the carbon because we can't attack the nitrogen. It already has its full octet. And what we need in this reaction is a source of proton from water. So our sodium hydroxide is, of course, dissolved in water. Bless you. To form our NH group, and then we get a second attack. And then what we eventually get to is NH2 as a leaving group. And again, we looked at this before. When we're comparing why do we have our NH2 leave versus our OH leave, and of course it's just a situation where N is a better leaving group. So we talked about this when we looked at reduction of our amides. It's also true here. We really need to look at what's the best leaving group in that case. So this leaves as our NH2 minus, and we get this protonation. So once this gets protonated, we can have that leaving group. Now these aren't necessarily easy conditions, and that's the other thing you have to realize about this reaction. This isn't a fast reaction. We need usually a good bit of sodium hydroxide for a long period of time. And in fact, like I said, I did the acid hydrolysis of amides. The base hydrolysis of the nitrile isn't that fast of a reaction. So usually you have to kind of make this happen pretty quickly. And we really can have extra H2O to really force this reaction forward, because it is going to be a reversible reaction as far as that's concerned. So typically what we do is has a bit more hydroxide and H2O driving the reaction forward. At the end of the reaction, once we form this, we typically will work up the reaction with a little bit of H3O plus that will neutralize any hydroxide left over and allow us to isolate the carboxylic acid. So fairly straightforward. Our nitriles can also react with the Grignard, but that is going to give us a slightly different product than what you might expect. So our first step, our Grignard is going to attack the carbon of the nitrile. That makes sense. It's our partial positive carbon. And what we form is this new carbon-carbon bond with our Grignard that attacked, and a carbon-nitrogen double bond. But we will not get a second attack, because if we do, then we'd have a nitrogen with a -2 charge if we pushed electrons onto that nitrogen, and that's really not likely. Nitrogen doesn't particularly want a -1 charge. It definitely doesn't want a -2 charge. So because that's unlikely, we pretty much stop at this point. And then what happens? Well, remember, with our Grignard, typically what we'll do is work it up with a little bit of acid. When we work this up with a little bit of acid, what's going to happen is we're going to actually end up with a ketone. So we only get one addition, but we don't retain the nitrogen. So we got to look at the mechanism a little bit for that as well. And of course, as soon as we add the acid, we're going to work up any Grignard that's left will react, but also this nitrogen doesn't want a negative charge, so it'll get protonated. And then it's going to be a very similar reaction to what we were looking at before, eventually getting to the point where we're going to end up with our ketone. So that's slightly different when our Grignard reacts with our nitrile than anything else we've seen. But the basics of it is the same. It's just the workup. And it's really hard to isolate this particular compound because once we put our acid in to protonate this conditions, we're pretty much going to drive the reaction forward to here. It's because our NH3 plus is such a good leaving group. So it's hard to stop. And we'll typically use this reaction to form a ketone with only one addition. There's other ways we can do that as well, though. We can use an acid chloride and the Yeoman reagent to do the same thing. So this is a route. Again, nitriles can be useful, but we don't use them as much. Of course, we can reduce the nitrile to the primary amine, and that's probably one of the most useful synthetic routes a nitrile is used for, to form the primary amine. So we can use lithium aluminum hydride followed by water, and we reduce completely to the NH2. So that's probably the most common route and the most common use for nitriles in synthesis. So this is just a review of the reactions we've talked about. The formation of the nitrile is pretty easy. We can either just do an SN2 reaction with our CN negative. That's easy, but we do add a carbon in that route because our carbon nucleophile is attacking. So notice the difference. We can also take our amide and react it with SOCl2. That's another route and a really good route. However, that route, we don't add a carbon. So that's our differences between those synthesis routes. If we want that extra carbon, we could go through cyanide. Also, cyanide is dangerous. And then we looked at a couple of reactions of this. We can hydrolyze them to the carboxylic acid. We can react it with the Grignard, and of course, we can reduce it to the primary amine, which is really useful synthetically. It's a good route to form a primary amine. As far as synthesis, we talked about a bunch of reactions, but a lot of the reactions we talked about were very similar. So remember, our acid chlorides and our anhydrides can pretty much do the same reactions, just our acid chlorides are a bit more reactive sometimes, and anhydrides easier to work with in the lab. So this looks like a lot, but it's a lot of repeating things that we've already seen and we've done. So when we're looking at synthesis, the first thing we want to consider is there a change in the carbon skeleton? Do we have any extra carbon-carbon bonds that we didn't start with? Do we have a change in functional groups? And we've learned a lot of different functional group transformations. In this chapter, and also pairing with our other chapters, we have a lot of synthetic tools. We can make a lot of different things in the lab. So let's look at this example. Here, as soon as you see CN, that's the nitrile, C triple bond N, so you need to recognize that. It's often drawn as CN and not actually drawn out as a C triple bond N. So you should always recognize it's a C triple bond N. And what we're doing is taking that nitrile to a aldehyde, specifically benzaldehyde. Now, a couple of things, we can reduce, or we can hydrolyze the nitrile to form carboxylic acid, but this final product isn't a carboxylic acid. So that's probably not going to be a good route to go through. So we need to look at what's likely. So first off, notice that we're not changing the carbon numbers, so we're not doing any new carbon-carbon bonds. We have the same amount of carbons in our starting material or our final product, but we are taking the nitrile to an aldehyde. So we can easily form the aldehyde if we have a acid chloride or an anhydride. And I'm showing it with the acid chloride, but remember we can do a lot of the same reactions with the anhydride. We only have one addition to hydrogen, bless you. So we did talk about a poisoned reagent we can use for a source of H negative with our acid chlorides. LiAlOR3 to stop at the aldehyde. Remember, lithium aluminum hydride will give us our two additions. Though, if you did that, you can oxidize it to the aldehyde, so that's another route. This is one step. But you could form the primary alcohol and then oxidize it. That's just giving you an extra step. And that would be with PCC, of course, so we stopped at the aldehyde. Now we can form the acid chloride through the carboxylic acid. So we can form the carboxylic acid, forming the acid chloride with SOCl2 impurity. Again, with the carboxylic acid, we could also form the anhydride. That's another route. I'm not showing it. But once we form the anhydride, we do the same step here. So we can form the anhydride by deprotonated the carboxylic acid with sodium hydroxide, then adding in this acid chloride. So we can form the anhydride if we wanted. And we can easily, either under acidic or basic conditions, where'd my plus go? This is showing acidic. We can also do basic conditions, react our nitrile to the carboxylic acid. And again, in this step, we're not changing the amount of carbons. So notice that. We always have to look out for that. There's two categories of bond-forming reactions. We can have our carbon-carbon forming reactions where the functional group remains in the same location. So, of course, our Grignard with our carboxylic acid derivatives. Remember, Grignard won't work with carboxylic acid because it will deprotonate the carboxylic acid. We'll get the two additions, but it isn't this carbon position. Our CuLi-R2, our Gilman, is again only going to give us one carbon-carbon bond in that position. Our nitrile also gives us the carbon-carbon bond to our partial positive carbon. The other route is where we're actually changing where the functional group location is. So if you look at taking our cyanide anion and reacting it with our bromine, we do form a new carbon-carbon bond. The functional group was this carbon, and now the functional group is the next carbon. So notice that where the functionality, so now the reactivity would be in this position, so it's in a different position. Whereas in all of these, the functionality remained in the same position for further reactions. Another example is if we take this, we form a Grignard and react it with CO2. That adds a carbon, but it also changes where the functional group is, making our carboxylic acid, but we do have a new carbon-carbon bond. So in those two different reactions, and another example of changing the functional group, which we're not showing here because that was a earlier chapter, but remember when we react our epoxide with it right here, that also moves where the functional group is. The functionality was here, but then we opened it up and the functionality is going to be in the adjacent carbon position. That wasn't in this chapter, that's why it's not on this slide, but we still need to know it, especially because your final's coming up. So when forming your carbon-carbon bonds, it's important to know where your functional group location is and make sure it's in the right location. So if we look at this example, we clearly have a new carbon-carbon bond. We started with one carbon, and we end up on the second carbon. So our functionality, our carboxylic acid, is actually on carbon 2. And we can go through two different routes to do that. Either we can just take our magnesium to make this a Grignard and react it with CO2 followed by H3O+. Remember, these has to be 3 separate steps. We cannot do a Grignard with H3O+ present, and that'll give us the carboxylic acid. Or we can react it with cyanide and then hydrolyze it to the carboxylic acid. That's 2 steps. Which is better? Well, it depends. It's often hard to do a Grignard in atmospheres where it's really wet and humid. So this might be a better route because you might get a better yield. Because any water in the atmosphere can stop it. Of course, cyanide can be hard to work with because it's dangerous. So there are 2 different routes for this one. You do always have to consider sterics, but overall, that's usually something you're seeing in the lab. A good rule of thumb is if you try to set something up and it's not working and it should work, you might want to consider sterics. You might have too much sterics for it to work. So I'm going to stop right here. I want to talk a little bit about amines. We're not going to get very much. I just want you guys to start thinking about it because that's all we're going to get to in this. I do recommend reading the amine chapter, especially before you're taking something like the MCAT. We didn't quite get as far as I wanted to, but we talked a lot about amines before and how they react. So it's a lot of reviewing again in this chapter because we looked at amines as nucleophiles in the last chapter. But before we talk about amines, I'm going to give you a quiz on chapter 21. Sorry. Okay, please pass it forward. So we're not going to really get into the reactions of amines or anything like that. I just wanted to have you think about the functional group and how it might react. That way, if you come across any problems with them, you will at least be able to figure it out. And anything we talk about from this chapter would be on the final. It won't be on the test on Wednesday. So, amines have a nitrogen with a lone pair, and it could have hydrogens. Typically, we have at least one R group, but we might have up to 3. And we already talked a little bit about how we label these as primary, secondary, and tertiary amines. So we're going to talk about that for a little bit. It's not going to be a very long discussion. But I just want you to understand the functional group. A bit about acidity with the functional group and basicity more importantly. And a little bit about naming, because we always need to know how to name these. So amines are derived from ammonia, NH3, and we call them primary, secondary, and tertiary based on how many R groups are directly attached to the nitrogen, which we've talked about before. This isn't the first time I talk about it like this. So there is a fourth distinction when an amine has 4 R groups. It's a salt. It has a positive charge, so it's called a quaternary salt. You sometimes might hear referred to it as the quaternary ammonium salt. I'll throw the ammonium in there. Because nitrogen doesn't mind having a positive charge. So depending on the conditions, we can have this quaternary salt. But for our neutral amines, we're looking at primary, secondary, and tertiary. As far as dissecting our functional group, we have a lone pair on the nitrogen for our neutral amines. So our negative charge is pretty much on the nitrogen in that region. And that's what we see. That's where we see that red area. So we have that lone pair and we have that electron density. So will it act as a base or a nucleophile? And that's dependent, and that's one of the things I really wanted to get into for this functional group, because that's one of the more important things. So amines often react as a base or as a nucleophile, depending on the amine. So what features are we looking at to determine whether it will act as a base or a nucleophile? One is the number of carbon groups attached, because the more R groups attached, the more sterics we have that are blocking that lone pair from being able to attack as a nucleophile. And of course, when it's acting as a nucleophile, it's attacking a carbon that already has some sort of things attached. So the more R groups we have, the least likely that we're going to get a nucleophile attack, because of sterics. Remember, in the base attack, it acting as a base, hydrogen's really small. So if we have big R groups, then that's when we get bases that are non-nucleophilic, things like our triethylamine and our pyridine, which we've talked about before. Also, other reagents. Of course, if we take an amine and we only have it in the presence of an electrophile and there's no base, it's either not going to react or it's going to react as a nucleophile. It's not going to react as a base if there's no acidic proton. So that can also contribute. So as far as naming, there's multiple methods for naming primary amines. The most common one for simple amines is just naming the R group and then putting amine in the end. So ethylamine, isopropylamine, cyclophosphamine, pretty straightforward. You hear these a lot. And that's pretty common as long as the R group is simple. If the R group isn't simple, then the parent is just amine, and then you just put the parent in front. So here it's heptane amine. And we want our amine to have the lowest functional group possible. So that one's also pretty straightforward. If we have a more functionalized carbon like a carboxylic acid or an alcohol, then our amine can be our side product or our substituent, and then it's just an amino. So for amino here, or here we're looking at para-amino. So amino is just, it's being named as a substituent. Fairly straightforward as far as that's concerned. There are some, if our amine is directly attached to the benzene ring, we call it aniline. So then we can name it based on that functional group as well, aniline. And we've looked at aniline before. This isn't the first time we see that name. We've seen that in chapter 18. If we have a secondary or tertiary amines, especially if the R groups are simple, we usually will have alkyl-alkyl or alkyl-alkyl-alkyl amine, depending on what the alkyl groups are. So trimethylamine here, we talk about triethylamine a lot as well, known as 3 ethyl groups. Or ethyl-methyl-propyl, just says we have an ethyl, a methyl, and a propylamine. Diethylamine. So we've looked at some of those. That's fairly straightforward. Now, if we have a longer chain parent and our amine is hanging off, how do we take these? Well, if this is our parent, this is just going to be our hexylamine, and then our chlorides are going to be named accordingly. But what do we do with these guys? Well, just like with our amide, those R groups would have a locant number of N. So we looked at that with amides. We could also see that with amines if our amine is named this way. Because this particular compound would be way too difficult to name based on this method. So our longest chain is our parent, and these are just going to be named N-methyl and N-ethyl. So that's also straightforward. We don't have that problem with the primary amines because we don't have R groups. So if we're looking at this molecule, the easiest thing, because this one is too complicated to name in an alkyl-alkylamine, is to choose our ring as our parent. So our parent will be cyclohexaneamine. We do drop the E though. And then we have that CH3 group hanging off. We'll call this 1, so this would be 2, our lowest numbering system. So our cyclohexaneamine. And then our isopropyl group is going to be attached to nitrogen, so it'll be an N-isopropyl. So 2-methyl and then isopropyl. I comes before M, so that's our alphabetical. And then if there is any stereochemistry, we have to specify, just like always. So fairly straightforward. With this one, ethyl-methylamine looks like this, so that's a secondary amine. That one's really the easy naming method because we have simple R groups. So again, the main thing when we're thinking about reactivity for these and properties comes from the fact that we have a lone pair on our nitrogen. And we're going to get a bit more about it being a base and also a little bit about its solubility. As far as the angles, we have 108 degrees because, remember, the lone pair takes up more space than our R groups. Even though it's still tetrahedral, it's really our geometry, if we exclude the lone pair, would be trigonoplanar. I'm sorry, trigonopyramidal. It looks like a little pyramid. One interesting thing, the amine can be considered chiral because it has, if it has 3 different R groups in a lone pair, that means it has 4 different things attached. A lone pair is different than our 3 different R groups. But we don't typically see chirality as far as optical activity because it's really easy for the amine because the trigonoplanar is not a very big pyramid, it's a shallow pyramid. So it's really easy for it to, at room temperature, interconvert from one to the other. Unlike our carbon stereocenters, which don't interconvert, our amines do, going through this trigonoplanar high-level intermediate. So that happens pretty easily. So we don't usually describe as our amines as optically active. But in pure definition, they can be considered chiral, as far as the fact that it has 4 different things attached. But again, typically it quickly interconverts, so we don't really see a pure enantiomer sample being isolated in most cases. So that's just a little side note. Solubility, that we have fewer than 5 total carbons. Our amines are typically soluble. Our primary amines are a lot more soluble, and secondary amines are a little bit less because primary amines have 2 hydrogens, so that's 2 proton donors. and then our lone pair is a proton acceptor. So as far as boiling point and solubility, our primary amines are more soluble and they have those higher boiling points because of the hydrogen bonding capabilities. As we go lower, secondary amines, tertiary amines don't have any protons, so they can still be water soluble depending on how many R groups, but they're not as strongly hydrogen bonding. And of course, they don't have as high boiling points because they don't have the proton donors, so they can't hydrogen bond with themselves. Which we've looked at all of this before, this isn't new. One other interesting thing about amines is they often don't smell good. As you might can see by these common names, putrescine and cadaverine. And it smells as you might think. And I haven't actually smelled those, but it's really, really bad. Also, amines can have very, very common unpleasant odors. A lot of amines, like triethylamine, it hurts to smell it. I don't know how to explain it, but if you accidentally smell it, it's like you can't hear anything, and it's weird. It's weird. I never like to accidentally smell any amines because it's like you can't hear. It's weird. So I really recommend always working in the hood with any amine-containing compounds. Pyridine isn't the worst smell, but it's still not pleasant. But it's not this unpleasant. Those are pretty unpleasant. Amines are generally stronger bases than alcohols because our nitrogen is less electronegative, so it's not holding the electrons as close. Also, the nitrogen doesn't mind having a positive charge if it has a positive charge once it forms the conjugate acid, because it's not as electronegative, so it's not as unstable to have a positive charge. And that's what we see. Amines typically act as bases and not as acids. So our pKa, as you can see, in this case, the carboxylic acid is pretty low. Our pKa of our conjugate acid isn't that low. So we're looking at 10 here. It really does not mind to deprotonate. Basicity can be qualified with pKa values. The larger the pKa of the conjugate acid, the stronger that it'll act as a base. The more stable this is, so the more the reaction is driven forward. You can also look up the pKb's, which are the, just like pKa's, the lower the pKb, the more stable, more likely it is to act as a base. So this is just some common amines and looking at their pKa's of the conjugate acids. And as you can see, they're all pretty stable pKa's, pretty high pKa's. The higher the pKa of the conjugate acid, the more basic these are. So most amines have a pKa of its conjugate acid around 10 to 11. So they're only weak bases. They're not as strong of a base as O negative. They're much stronger than OH, of course. So they're not a strong base, which is why we often use things like pyridine, things like our triethylamine. And again, our triethylamine, which is here, we've talked about it a couple of times. It has a pKa, again, in that range, but it tends to not be very nucleophilic because of the sterics. Why did it go back? As far as water solubility, if we have a lot of R groups, we lose water solubility, but we can protonate them and make them water soluble, which we use often in the lab in our washing, where we will put a weak acid in, and then we'll protonate our nitrogen, giving it a positive charge and making it pretty water soluble. So even if we have a larger R group, in acidic conditions, our amines are water soluble. Now there are some amines that are less basic. For example, some of these, notice their pKa's at the conjugate bases are a lot lower. That means that pyridine is not as basic as our triethylamine. So that can happen. And the reason why, if we look at some of these, well, perol has it's very much not basic. Pyridine's okay. If we look at these three, they don't really want to give up their electrons, and they don't really want to give up the lone pair because it's in conjugation with the ring. So remember, resonance makes the lone pair more stable. The lone pair is more stable, it's less likely to be given up. But I really want to look at parole. We've talked about this before. So this is our lone pair being stabilized by residence, so it's less likely to be given up as a base. But parole I wanted to touch upon. This is the last thing we're really going to talk about. Why is it so not basic? And the reason why is going into what you're going to be tested on Wednesday, on the fact that it's aromatic when it has its lone pair, and then when it has that positive charge, it's actually anti-aromatic. So the parole really doesn't want to give up its lone pair. Whereas pyridine is still aromatic. So that's why pyridine is still basic. So remember that aromaticity can affect our basicity. If our lone pair, and of course with pyridine, our lone pair isn't participating in aromaticity, so we can give it up. But parole is, so it really doesn't want to give it up. So that's what we're going to learn about amines. And again, none of this is going to be on the test on Wednesday. I do have any quizzes if you haven't picked up any quizzes here from other quizzes. A lot of you have all your quizzes. And don't forget we have a review this afternoon. You can grab it. That's what I wanted.